All right, in our final recording for the weekend, I just wanted to make sure that we covered some of the material that we couldn't get to on Thursday in class. We're going to run through the last few slides that really just talk about energy and how it relates to environmental science. And a lot of it has to do with the two laws of thermodynamics that we will be examining. I'm going to use a red pen here. Okie dokie. First one. Simple first law of thermodynamics, just like the first or the law of conservation of mass. In the first law of conservation, or in the first law of thermodynamics, we can call it the law of conservation of energy. Another way of saying this is that energy is neither created nor destroyed. That is to say, you can't get something from nothing. Energy can't be created anew, and we don't get rid of energy, but it's always transformed. So whenever we're talking about environmental systems, we have to ask ourselves, how is energy transformed in this system? How is it transferred from one organism to another, or from one system to another? Or do we have to import it from outside the system, but we can't create it anew? Okay? Just like if we're looking at a car, there's energy in that car, which is specifically in the gasoline of that car. There's energy there in those bonds in the gasoline, in the oil. And so we are able to release that stored potential energy and turn it into something of energy in motion, kinetic energy. So we take the potential energy in that, or the chemical energy in the gasoline, and turn it into useful energy, or energy that we can use, known as motion, kinetic energy, which of course moves the car. But of course, we don't transform the energy entirely into motion, because some of the energy is lost, and we call that waste energy. And the waste energy is lost as heat. From the friction that we find in the engine, in the tires, between the tires and the road, and the tires and the brakes. We also lose energy in the form of sound, from sound energy, like the tires on the surface, and from the pistons moving in the engine, we hear sound from that, so there's energy transformed there. All of that energy, that heat, the motion, the sound, all of it comes from, is stored, it's transformed from the potential chemical energy in gasoline into useful energy and waste energy. So that's our first law of thermodynamics. We're not creating anything new, we're just releasing it, transforming it from one thing to another. Which brings us to the second law of thermodynamics. We're going to call this the law of entropy, and we'll define entropy in a second. But the second law of thermodynamics, in sort of colloquial terms, tells us that when energy is transformed, the quantity of the energy remains the same. Well, of course, that's nothing new, because that's the first law of thermodynamics. The quantity of energy remains the same. But the important part in the second law of thermodynamics says that its ability to do work diminishes. And of course, here's that term again, work. Okay, its ability to move things, or ability to cause displacement, for example, diminishes. So let's take a look. If we've got our energy factory or something like that, we're generating lots of energy. Of course, the total amount of energy remains the same. Some of it, of course, is lost as heat, but some of it can do work. That's great. And so we've got all of that energy, and all of the energy that can do work and sent through the power lines, some of that is lost somehow or another. And we have the leftover, the remains, able to do work, but of course that's less than what was actually put into that system. And then of course that energy used to power a light bulb, for example. The total energy remains the same, a lot of it is lost. Only a little bit of it is able to do work. So as we move down our sort of chain, or down the hierarchy of energy, the amount stays the same. We always started with this total amount of energy, but its ability to do work diminishes because we lose energy to the environment, which brings us to, of course, the idea of entropy. Entropy tells us that all systems move towards randomness rather than towards order. That this randomness always increases unless new energy from the outside of the system is added to create order. Another way of saying this is that things will disintegrate. We will lose, nothing is 100% efficient because of entropy. Nothing is 100% efficient because of entropy, because the system that we started with will disintegrate in some way, shape, or form. The total amount of energy some of that total amount of energy will always be lost due to heat, due to sound. We can't perfectly transform one form of energy to another form of energy without losing a little bit in that translation or in that transformation. That's what entropy tells us. And of course, then that brings us to the idea of energy efficiency. We hear these things a lot. How efficient is this system? Well, energy efficiency we're going to define as the ratio of the amount of work that is done to the total amount of energy that was introduced into the system in the first place. Okay, so we see two different kinds of fireplaces. One is more efficient than the other. Let's imagine that we're introducing the same amount of energy, okay, to the system. In this case, let's introduce this amount of wood to this fireplace, and let's introduce it to this fireplace. We're going to ignore this amount of wood for a second. If we introduce this amount of wood to our first fireplace, we're not going to get a lot of usable heat because a lot of that heat escapes. All right, that is to say, it's not a very efficient fireplace. Whereas if we introduce the same amount of wood to this modern wood stove, we're going to get a lot more heat generated because it's more efficient at converting the total energy introduced into work that we want to be done. That's what energy efficiency tells us. Which is to say, if we want to create an equal amount of work done, we could actually use fewer resources, which allows us to use less wood to create the same amount of heat. All right, of course, this is going to be more efficient. It's going to cost us less in the long term, which is why we ultimately want more efficient technology in our environment and more efficient materials to be used in our environment as well. All right, from this lecture then, we come back to our energy problems, because our third energy problem that we look at talks about energy efficiency. Okay, I'm not going to work out this problem in total, but I want to point out a few things now, given our discussion about entropy and the second law of thermodynamics, as well as the first law of thermodynamics. I'm going to change my pen color one more time. Here we go. Okay. It tells us that a 100-watt light bulb is 20% efficient. Of course, and so we know a few things. Our power in wattage is 100 watts. That our efficiency, I don't know how we want to call it, how do we want to say that, but we've got 20% efficiency. I'll just go EFF. And that, remember, that 1 watt is equal to 1 joule per second. So our problem tells us, therefore, that 100 watts is equal to 100 joules per second. Cool. So now we ask ourselves in question A, how much energy does this light bulb use in 12 hours of operation? Okay, so now we have to convert a few things. We have to convert our power from watts to joules per second. That's going to be an important thing here. And then we want to be able to convert from seconds to hours. Hours. And then we know we're using 12 hours. So you're going to go from, that your conversion factor from seconds to 1 hour, and then you're going to go from 1 hour to 12 hours. That's the important piece of information that you're going to need to answer part A. That should be review now, because we've done that in the first two problems. But in part B, it asks us how much energy does the bulb actually convert to light into that work in 12 hours. Well, you're going to use that energy, the amount of energy you calculated in part A, the amount used in 12 hours, and you're going to talk about energy efficiency here. You can say, for that total amount of energy, let's call that X joules of energy. You're going to convert, saying, I know that I know that my system is 20% efficient. So for every 100% of energy that I get, or that is introduced, only 20% of it is actually used to create light. So that's my energy efficiency conversion factor, for example, which is just to say we're multiplying our answer by 20%, or that is to say by 0.2. Okay, that's pretty simple, but it just introduced the idea of energy efficiency in our ability to answer these problems. Then, of course, we can convert our answers in joules and make them into kilojoules per kilowatt hours. And we've already created that conversion factor. We already knew that 1 kilowatt hour is equal to 3,600. What did we say? Kilojoules per sec. Or excuse me.